Welcome to Unit 9, Section 6. This is graphs of polar equations. Now, previously, you are familiar with plotting things in XY. That is rectangular. Now, we will be doing polar, which is r theta. Okay. Let me write that. R theta. That is polar, or I think your book also calls it trigonometric form. Everybody will call it polar outside of the class, so I'm just going to say polar. And that is a circular. Remember where r was the radius? So we had the radius and theta was the angle measure. So that is what we are going to graph. Now, one way that you guys will easily do this is by plotting points. So what that means is you would make a table of your r and your theta. And you just fill them out. And then when you go to graph them, remember that this graph is circular. So we would graph it on this. Where these correspond to r. That's your r. And these angles are your theta. Now, one way to confirm this is you can convert to rectangular. And you can confirm that. You can use polar mode in your calculator. Or you could use parametric mode, which we learned about previously with T, where you're plugging something in for something else. So let's see if we can get to polar mode. Here we go, mode, polar. We're going to second quit. We will go to y equals. Now, if I were to give you this equation, r equals sine theta, or actually let's make it a little more difficult. So we're going to have r equals 4 sine theta. We'll go with that one. Now we can put this in here, 4 sine of theta, graph, zoom. You're going to go to zoom square. Well, what about zoom standard? There it is. And if we want to have a look at it, we can do zoom fit, and it would fit that. So it looks like an oval. Would actually be more of a circle, but we could change these things by changing the way it looks. So let's see if we would be able to window 360, 7.5. The x-min, we'll call that -4. The y-max, we'll call that 4. The scale, we'll just do everything -4. See if we can See what that looks like. Scale is 1, graph. Oh, still ovally. That's okay. This is how you would graph something in a calculator if I've given you this. Now notice another thing, since they're cyclical, they can be symmetric with respect to pi over 2, the polar axis, or the pole. So when it says respect to the line theta pi over 2, that's this guy, right down the middle. So this is symmetric. So that means that if I have r and theta, it's the same thing as r pi minus theta or minus r minus theta. So the polar axis is this axis right here. So now I can have r theta, and we'll get an equivalent equation if we use r negative pi or negative r pi minus theta. Now symmetric with respect to the pole. Remember, the pole is this dot right in the middle. Now if we get an equivalent equation when we use r plus theta or minus r theta, then it is symmetric with respect to the pole. Let's have a look. So I'm going to actually do a quick example of that previous one. So let's say we have r equals 2 sine theta. Now how I would do this is I would just go down the list. So my r would be replaced. Here, we need to use r. Actually, we'll use this one. Negative r negative theta. So we have negative r gets replaced with r, 2 sine negative theta. So then r equals negative 2 sine negative theta, and we know that sine negative theta is just equal to positive sine or negative sine theta. So that just becomes 2 sine theta. So it is symmetric with respect to this axis. Now what about this one? We can try replacing it with this. So that's r equals 2 sine negative theta equals negative 2 sine theta, which is not equal to our original equation. Now what about the pole? Well, if we replaced it with just a negative r, we'd have negative r equals 2 sine theta. Getting rid of that r equals negative 2 sine theta. So yeah, it's not the same. So this one is only symmetric with respect to the line theta equals pi over 2. That's a little example. Now, quick tests for symmetry in polar coordinates. So the graph of f of sine of theta is symmetric with respect to the up and down axis. So the line theta equals pi over 2. So what we would normally know as the y. And this graph is symmetric with respect to the polar axis, what we would normally know as an x. Okay. And these are quick tests for symmetry. Let's see. I don't really have an example for that one. Okay. Some curves have maximums and minimums. So let's see if we can talk about, oh, actually, I have an example, the example I was looking for. So we're going to analyze the graph of r equals 2 cosine 3 theta. So one thing I can do is I can graph it on a calculator, which is all fine and dandy, but I also would like to see you replace things here. So I'm going to put that into the calculator to see what we get. 2 cosine 3 theta graph. Whoa, it's an interesting one. So let's have a look at this. Is this symmetric with respect to the line theta equals pi over 2? Well, it does not look like it. But we'll go ahead and we'll have a look and see what's going on using those rules. So if we want to test for the line theta equals pi over 2, we've got to turn r and theta into negative r, negative theta. So we'll try that one. So we're going to have negative r equals 2 cosine negative 3 theta. Now, what can we do here? This is not going to be equal. This is not going to be equal at all. Yeah, this will come out to some positive 2 times, we would use a product here. You don't have to do that, but obviously I don't think that one is really going to, yeah, we'll just take the graph's word for that one. Now, what about for the line or the polar axis? So the x-axis, does it look like it might be symmetric with respect to the x-axis? So let's zoom in, and we're going to go all the way down to the bottom, and we're going to do a zoom fit. Well, yeah, it looks like it could be symmetric to the x-axis. Yeah. So that would be the polar axis. So r and theta get replaced by r negative theta. Let me pull out some formulas. So let's see what we have, or we can replace it with negative r pi divided by theta. We will go ahead and use r negative theta. So I'm going to have r equals 2 cosine negative 3 theta. Now, I'm going to take, okay. So if I don't want to deal with this 3, I'm going to pretend it. I'm going to say u is my new angle of negative 3 theta. So then I have 2 or positive 3 theta. So then I have cosine negative u. Now, cosine of a negative will actually just give us the positive. So that'll equal 2 cosine u. which will equal 2 cosine 3 theta, which is equal to the original r, which is what we're going for. So it's symmetric with the polar axis. Now, is it symmetric with the pole, the very, very center? I don't think so, but we'll have a look. R and theta are going to get replaced by, the easiest one is negative r theta. So that gives us negative r equals 2 cosine 3 theta. So r is going to equal negative 2 cosine 3 theta. And that's not, I can't make that equal to r equals 2 cosine 3 theta. So it's not. So it's not symmetric to the pole, and that's the center. Nah, les maçons. So this is a bizarre graph that turns back in on itself, as you can see. So it's like a circle with like a squished side, and then it slowly becomes more peach shaped, then it kind of looks like a butt. And then it creates a little tiny egg-shaped graph right in the middle of your original graph. So the inner loop is when AB is less than 1. This heart-shaped, oh, I guess I could have said heart-shaped instead of butt-shaped. This heart-shaped graph, a cardioid. If you'll notice, it sounds like heart, right? This is a dimpled limacon, and this is a convex limacon. Remember these. So let's see if I wanted to graph one of these, if I just want to make one of these up. So if I need something with an inner loop, my A divided by B has to be less than 1. So my B has to be greater than my A. So let's try R equals 2 plus, and then my B has to be greater than that, 2 plus 5 cosine theta. Let's graph that. 2 plus 5 cosine theta. Ooh, what does that look like? So let's do zoom. We don't want the fractions or quadrants. We want zoom fit. See how it's got that inner loop? Now what about a cardioid? So our A and our B have to equal 1, so that A has to equal B. So I'm going to take now sine. R equals 2 plus 2 sine theta. We'll try that one. 2 plus 2 sine theta. All right, now let's see what this looks like. Zoom, 0. Oh, look at that. A cardioid. And of course, you could play around with the calculator with these. So if we need A divided by B is between 1 and 2, but not equal to, there we go. So then that means A has got to be greater than B, but less than 2B. So if our B is 2, A has got to be between 2 and 4, so we can make it 3. That's how that works. If you wanted to build an equation, and then you can use any one of these. Now, if you wanted something that would satisfy this, A would have to be greater than or equal to 2B. So if our B is 3, then A has got to be greater than or equal to 6. And you can build an equation like that. Rose curves. Notice that this is what we had in that previous problem. So if n is odd, so notice here n is 3, we have exactly n petals, 3. Where's another odd one? Here n is 5. We have 1, 2, 3, 4, 5 petals. Now, notice that when n is even, greater than or equal to 2, can't be negative, can't be 0. So here n is 4. So we have 2 times n equals 8, because n equals 4, petals. So you have twice the n petals. 1, 2, 3, 4, 5, 6, 7, 8. See? This is n, so you'll have 4 petals so when n is 2. 1, 2, 3, 4. And notice that A is the length of one of these petals. Right there, here's another one right here, and they'll all be the same length, so they're all going to be A. A is length of petal. This is a pretty cool one. I guess I'll show you what that looks like. Let's try n equals 5 is the length of our petal. We'll go with cosine. 5 cosine. If we want, well, we'll do 10 so that we have 20 petals since it's an even number. Ooh, look at how weird that is. Let's see. Ooh, look at that. That is just crazy. Well, yes, that's an actual legitimate graph, guys. It's called rose curve. These are circles and lemniscates. So a circle, yeah, you guys kind of know what circles are. That one's not too bad. Now these lemniscates, they're propellers. See how they look like propellers? Like on an airplane, around and around and around and around. So it's going to be at an angle when it's sine, and it's going to be along the polar axis when it is a cosine. And these are some pretty interesting graphs. So we're going to analyze the graph of r equals 3 cosine 2 theta. So what does that look like to you? What form does that look like to you? Well, nothing is squared, so it's not a lemniscate. There is something attached to the theta, so it's not a circle. There is no plus or minus, so it's not a lemniscate. What does that leave? A rose curve. That's right, a rose curve. So here we have A is equal to 3. N is equal to 2. So since N is even, we will have 2 times N petals. So we're going to have 4 petals. Those petals will be symmetric with respect to the polar axis. Yes. So do you remember how we said, I think G of sine is going to be symmetric, or I'm sorry, G of cosine. So when you have a function that has cosine in it, you should check for symmetry with the polar axis. So the length of the petals is 3, since that's A. Now let us put this into our calculator as 3 cosine 2 theta. And we'll graph that. Good. Zoom. 0 means fit. So this is what this looks like. Where this length is 3, and you have 1, 2, 3, 4 petals, which means that this right here is 3. So if we were to graph that on a circle, it would be graphed. This is kind of what you would see. Weird, right? It's like a box fan. Now we're going to analyze this graph. The first thing that we should notice is that it's squared. This will always produce a lemniscate. Remember, that's the propeller. So we can immediately say that the length is equal to A, and here 9 is equal to A squared. Remember, because it's R squared equals A squared sine 2 theta. So that means that A is 3. So let's see what this looks like. Y equals, we'll have to go with the square root of, let's see what that will like, A squared 2 theta. So if I took the square root of that, that would give me plus or minus A root sine 2 theta. So let's see what that looks like. So we will go with, A is 3, so we'll go with 3 root sine 2 theta. And I'm going to delete this, delete this, delete this, and we'll see what this graph looks like. Oh, all right, well that gives us a propeller. And that's what that looks like. So we can say it's something like that. I'm terrible at drawing these propellers. Yeah. So this length is 3. All right. All right, and remember, when you analyze these things, you can use your graphing calculator. I will want you to back it up with some calculations for symmetry, if that's what the question asks for. Don't just eyeball it, but if you believe it's symmetric with respect to a certain thing, you know, do show it, please. And what else? Yeah, mainly just doing your calculator and making sure you know what A and B are. All right, that was Unit 9, Section 6, and I will see you in the next video.